So today we're going to talk about the first law of thermodynamics, and we're going to derive a couple expressions related to the first law of thermodynamics. So first, we're going to work with this first situation, which tells us to derive an expression for the amount of heat that must be added or removed for an isothermal reversible expansion or compression of an ideal gas. So over here, what I've done is I've written down the first law of thermodynamics, and we defined the first law of thermodynamics as this is the change in internal energy. We have a component which is related to the heat added or removed. And we have this component which is the work done by the system. So let's go ahead and try and substitute in some simplifications here. So first things first, we're going to denotate that this change in heat is going to be reversible since we are working with a reversible reaction. So this is going to be reversible heat plus, and since we are actually not, the work is not being done by the system, but instead we're going to be doing work to the system by the viewpoint of the system itself. This is going to be negative work done by it, and we're going to equate this differential amount of work to the external pressure times dV, the differential change in volume. Now, what we can end up doing with this change in an internal energy component is we're going to equate this to CV times dt. And we are going to go ahead and make a couple assumptions here, which is that our external pressure is going to be equal to our internal pressure. And since it is an ideal gas, we're going to go ahead and apply our ideal gas law. So we will have, we're going to assume 1 mole of gas. So let's go ahead and just go RT over V. So we are going to subtract RT over V dV. Now, since we're working with an isothermal system, we can deal with this temperature factor here, and we're just going to set that equal to 0. Since, of course, it is an isothermal reaction, we are not changing any temperature. And so when we go ahead, we're going to rewrite the rest of this, minus RT over V dV. What we can end up doing is we're just going to equate both sides. So dq rev is going to equal RT over V dV. And since we are working with differentials on both sides now, what we can end up doing is we're going to integrate on both sides. On this side of the equation, we're going to go from 0 to the final heat, or the reversible heat. And from here, we're going to go to some initial volume to some final volume. And so when we go ahead and do this, we get that Q reversible for our isothermal expansion or compression is equal to RT times the natural log of the final volume over the initial volume. And this happens because R and T are going to be constants, and it is 1 over V, so essentially it is just going to be this natural log function that we have here. So now that we've gone ahead and derived the expression for an isothermal compression or expansion, let's go ahead and take a look at the adiabatic counterpart of this. So isothermal means that there is no change in temperature throughout the time of the reaction. And so adiabatic, when we talk about an adiabatic expression or compression, what we were talking about is the fact that we don't have any heat transfer throughout the reaction. And so there is no change in heat within our system. So if we go through, let's go ahead and rewrite our first law of thermodynamics. I'll go right here. If we go ahead and rewrite this, so we have change in internal energy equal to the change in heat minus P external dV. We go ahead, we look at this component, and we say we don't deal with that anymore. That's 0. And from here, we can go ahead and start our simplifying process. So now from here, things are going to look pretty similar to our last simplification. We're going to go ahead, we're going to set this side equal to CV dt, which we can do because we were dealing with an ideal gas, is equal to, remember we had over here, we had defined this entire, um, we had had this entire conjecture where we had the external pressure equal to the internal pressure. Thus, we could use the ideal gas law and the internal pressure to go ahead and assume 1 mole of gas. So we have RT over V. So we're just going to simplify this the same way, where we have RT over V dV. And what we have here now is a separable differential equation. So what we want to do, let's go ahead and get T over to this side. To do that, we're going to have to divide by T on both sides. So now we have CV times dt over T is equal to negative RT, or sorry, just negative R, because now the T is on the other side. Negative R times dV over V. And just like last time, what we're going to go ahead and do, we're just going to go ahead and integrate both these sides. CV and R are constants, so we don't really need to deal with that. And so when we go ahead and find our limits of integration, we're going to go ahead and get some initial temperature T1 to some final temperature T2. And we're going to do the same for the volume, some initial V1, some final V2. So when we go ahead and integrate, we have CV times the natural log of T2 over T1. And now when we look at this side, we have a negative coefficient out here up front. If we go back to our logarithm rules, we know that if we were just to have some natural log of x over y, if it was a negative natural log of x over y, it would just become the reciprocal of that. So for this one, what we're going to go ahead and do is we're going to go r times natural log of v1 over v2. And that is because we have that negative coefficient out the front. So now that we've gone that far, all we really need to do here is we're just going to bring this r over to this side. So we're going to go CV over r is equal to, CV over r natural log T2 over T1 is equal to natural log of V1 over V2. And now, if we go back to our exponential rules, we know that if we multiply a logarithm by some coefficient, that coefficient then becomes the exponent of that. And so what we are essentially looking at is natural log of T2 over T1 to the C, where did 3 come from? CV over R power equal to natural log of V1 over V2. And so now we put all of this to the e power. These will cancel out our natural log expressions. And so what we end up with here is T2 over T1 to the CV over R power is equal to V1 over V2. And this here is going to be our temperature volume relationship for an adiabatic system. So we've already covered the first part of A2, so let's go ahead and cover the second part, which is going to be the pressure-temperature relationship of an adiabatic compression or expansion of an ideal gas. So we're just going to work off of this equation here. And what we're going to do is we're going to go back to our ideal gas law and recall that we have PV equals nRT. Now for this, we're just going to assume n equals 1 like we have been. So we have P1V1 equals RT1 and P2 V2 equals RT2. If we go ahead and try and get T1 and T2 by themselves, we end up with P1V1 over R equals T1 and P2V2 over R equals T2. Now if you look back, If we look back here, we see that we have T2 over T1. So let's go ahead and try and recreate that here. So if we have T2 over T1, we are essentially getting P2 V2 over R times, and since we're dividing fractions here, what we can do is multiply by the reciprocal of the other fraction, which is going to be R over P1 V1. Our R's here cancel out, and we are left with P2 V2 over P1 V1. So let's go ahead and plug that back into this equation here. So we have P2 V2 over P1 V1. So we have P2 T2 over V1 to the CV over R power is equal to V1 over V2. Now from this point onwards, everything we do is just going to be trying to simplify this down and trying to get pressure and volume on either side of the equation. So let's go ahead and try and do that. So the next thing we should want to do here is we now have this entire fraction to this exponent over here, and we have fractions on both sides. So the smartest thing to do here would to cross multiply everything around here. And when we go through with our cross multiplication, we get P2 to the CV over R power times V2 to the CV over R plus 1 power. And that plus 1 is coming from this V2 that we are multiplying on this side. And so we're going to go end up doing the same thing for the other side. P1 CV over R times V1 CV over R plus 1. And we can also rewrite this further by just rewriting this as into a single fraction. So P2 CV over R V2 CV plus R over R. Same thing on this side, CV over R V1 CV plus R over R. Now, let's go off on a bit of a tangent and let's talk about enthalpy. Whoa. Can't write today. Enthalpy. Now, enthalpy we can rewrite as the symbol H is equal to the change in internal energy plus PV. And since we are dealing with an ideal gas, we can end up going back to our PV equals RT relationship with assumption of 1 mole. And we can rewrite this as H is equal to U plus RT. And now let's go ahead and take the derivative of this entire function with respect to temperature. So dH dt is equal to du dt plus R. Now, we have a couple definitions here. The derivative of enthalpy with respect to temperature is known as Cp, which is the specific heat at a specific heat with a pressure standpoint, is equal to Cv, which is what we've been using this entire time, plus R. And so we see that we have a couple Cv plus R's over here in our equation. So let's go ahead, plug and chug that through. So now what we have is P2 Cv over R times V2 Cp over R. We'll do the same thing on the other side. Cv over R, V1 Cp over R. And that's where this law of enthalpy comes into play. Now, one of the last things we're going to do for this volume pressure relationship is we have a whole bunch of R's here that we can easily cancel out if we put everything to the R power, just like so. So let's go ahead and do that. So we have P2 Cv V2 Cp is equal to P1 Cv V1 Cp. And then from here, we're going to put everything to the 1 over Cv power just to get rid of the Cv on the pressure. 1 over Cv. So now we just have P2 V2 Cp over Cv is equal to P1 V1 Cp over Cv. Now there's something very special about this relationship here. And the special thing about it is something that we call the heat capacity ratio. Heat capacity ratio, which is often denoted by the Greek letter gamma or K. Personally, I prefer to use gamma because it's cooler in Greek, so why not? But essentially, what we have gone ahead and found out here is that we don't really even need to look at 2 states. We could look at a whole 3rd state, 4th state, 5th state. We could look at as many states as we want. And so what we go ahead and find out here is that PV to this heat capacity ratio, that's just some constant. The relationship between this, that, and the heat capacity ratio, everything about that is just a constant. So we can look at as many states as we want, and that pressure volume relationship is just going to be held constant. And so when we look at this relationship, we can also turn back and go ahead and find that pressure-temperature relationship. This is kind of a relationship. This is a relationship for the volume temperature. We found a relationship for the pressure volume. And now the last step that we can go ahead and do, here it is. We're going to go ahead, we're going to find the pressure temperature. So let's go ahead and do that next. So now let's go ahead and we're going to go back to our ideal gas law. And we're going to go ahead, we're going to isolate for volume. And volume is going to be equal to RT over P. We're assuming 1 mole of gas, of course, as always. And so we have P times RT over P gamma is equal to, I'm going to call this constant C, just because it is a constant, and it's just going to be a culmination of constants in the very end. So what we have here is we have P times R to the gamma power, T to the gamma power, P to the gamma power equals C. We're going to end up, we're just going to divide by R gamma on both sides. R gamma. And on this side, it's not going to matter much because, again, C is a culmination of constants. So that's not really going to matter. What really matters is that we're canceling out our R to the gamma over here. And so we are left with, since this is P to the first power and this is P to the gamma power, we have P to the 1 minus gamma times T to the gamma equals C. And if we want to isolate T by itself, we are finally left with our T is equal to the culmination of constants times P to the gamma minus 1, because we are dividing on both sides. And since we are going to take the gamma root on both sides as well, we're going to divide this by gamma. And this, ladies and gentlemen, this is our pressure-temperature relationship for an adiabatic compression or expansion using an ideal gas.